talking to you about water quality in flowing water bodies. And I introduced this idea of different nitrogen species, and we were looking at single point discharges. And I also showed you an example of multiple point as well as non-point discharges of wastewater and how they have an impact on the nitrogen species inside the river. So based on that, based on these concepts, there is this concept about nitrogen, and then there is another concept that we have already covered, and that is coliforms. And the third concept is about dissolved oxygen as well as BOD. So now that you know the terms, so if you look at the very first, or let me back up a little bit over here. This table shows you the use-based classification of surface waters in India. So CPCB has this, you can call it ambient water quality, or you can call it use-based classification. Now, this use-based classification is based on particular water quality parameters. So these water quality parameters will tell you whether the water is good enough for, let's say, drinking or outdoor bathing, what is the degree of treatment that is required, and what are the other uses that the water is going to be used for. So in general, we all know that for drinking water, we want the highest quality. We want zero coliforms. So in the ambient water, I want that the coliform level should be zero. And this is measured in terms of MPN. MPN stands for most probable number. So number of coliforms, most probable number of coliforms per 100 ml should be 50 or less. And this kind of water can be called the best quality of water. It can be used without treatment. And the only treatment that is required anytime you are going to store the water, which is the case in all water supply schemes. So since storage is part of all water supply schemes, you have to disinfect it. Okay. So the first parameter from a health perspective, louder please. There's a problem, right? Hello? Are you able to hear me?
Yes, ma'am.
Okay. What was that issue?
I think someone unmuted their mic.
Okay. All right. I can't see anyone, so it's very difficult to understand what is wrong. Okay. That's my point here. Yeah. No. Okay, we're back right there. Okay, so like I said, the best possible water is where you can use it without treatment. And our goal in terms of coliforms is that it should be zero. So if it is less than 50, then you can use it after disinfection and bring it down to zero. We know that pH in general should be around 7. So we have 6.5 to 8.5, which is the tolerable range. So this is what we call acceptable water quality. I've also mentioned to you about dissolved oxygen, that dissolved oxygen is basically an indicator of the amount of organic matter present in water, and it's also an indicator of the health of the ecosystem, the aquatic ecosystem. So these aquatic species, generally fish and so on, they need at least 6 milligrams per liter or more. So this is considered good quality water, and that is class A. Now, if the DO level is fairly high, then you know the relationship between BOD5 and DO. So you know that the BOD5 is more or less going to be low. And in this case, we are saying that it should be less than 2 milligrams per liter. If the water quality does not match any one of these 4 parameters, then what are the acceptable ranges for these 4 parameters? So total coliforms per 100 ml less than 500 will give you class B. pH remains the same, 6.5 to 8.5. Dissolved oxygen comes down a little bit to 5 milligrams per liter or more, and BOD5 goes up 3 milligrams per liter or less. So that is where you can have outdoor swimming and bathing and all that kind of thing. If the level of water quality is poorer than that, then you have total coliforms less than 5,000, pH between 6 and 9. You can see that the range has widened. Dissolved oxygen level goes down. At this point, certain fish and other species can survive, but it's the more sensitive species are unlikely to survive under these conditions. So this kind of water has to be treated, and that's where we have conventional water treatment and of course disinfection. So anytime you're going to use water for drinking purposes and you're going to store it for any amount of time, disinfection is an absolute essential. Then we have BOD5 that can be the same 3 milligrams per liter or less. Now, supposing the water quality is really bad and the BOD level is higher than 3 milligrams per liter or more, and it's unfit for drinking, is it good enough for species, various aquatic species? So wildlife, fisheries, all these things, can they thrive even under those conditions? If the answer is yes, then these are the parameters that are checked. So pH between 6.5 to 8.5, dissolved oxygen 4 milligrams per liter or more, and you can see free ammonia 1.2 milligrams per liter or less. What does free ammonia indicate? Free ammonia is generally indicative of fresh wastewater discharges. And when I say wastewater, I mean municipal wastewater. So when there is municipal wastewater discharge, that organic nitrogen is first converted to free ammonia. And you can see that free ammonia levels, if they are high, then it's unfit for drinking and it's okay for certain types of aquatic ecosystems, but they're not going to be very healthy ecosystems because some of the sensitive species, like I said, will not be able to thrive. If it is poorer than even this class D, what are the acceptable limits? So pH 6 to 8.5, electrical conductivity. Now electrical conductivity is related to dissolved solids. So we have total dissolved solids. This total dissolved solids is kind of difficult to measure in the lab. It takes a long time. It takes minimum 24 hours to measure in the lab. And electrical conductivity is very, very easy to measure. It's an electrode-based test. So you have a portable electrical conductivity meter. It's about just slightly more than a digital thermometer or a pen-sized probe, and you dip it in water, you get a reading, and that tells you the ionic strength. It literally is an indicator of the ionic strength of the water. So you can call it TDS. We have a conversion equation for converting electrical conductivity to TDS. But what it really indicates is the ionic strength of the water. And if that is fairly high, so maximum is 2250 moles per centimeter, micromoles per centimeter. And then you have sodium absorption ratio, maximum 26. This is again, now these two parameters, 3 and 4, are for agricultural use. So that's why you see that the water may be unfit for drinking, bathing, and even for wildlife, but it may be okay for irrigation. So the last two parameters, sodium absorption ratio and boron, are related to agricultural use. Just to give you some idea of how to use this data, so here we have data for the Ganga. Okay, now this is fairly old data. It was collected in 2011. So CPCB had put out in the public domain, they put out some data for only 1 year, but it was comprehensive for the entire country. So all the rivers and lakes and ponds and so on for the entire country was shown in this database. So we got access to it because it was on the internet. Normally, it's very difficult to find this kind of data, but it had BOD and DO levels along with several other parameters. So one of the BTech students, he put it all together and made these graphs. So you can see the BOD and the DO for the Ganga River starting all the way from Gangotri to Diamond Harbour. And you can see the level. So for class B, BOD is less than equal to 3 milligrams per liter, and DO for class A is more than 6 milligrams per liter. So you can see that in many parts of the river, especially all the way from Palwal to I think it's almost this is Etawah and then this is Allahabad. So almost this entire stretch is highly polluted. The BOD is class it's mostly in class C or worse. And in terms of DO, it's the same story. So all the way from Nizamuddin Bridge is, I think, downstream from Delhi. So yeah, and it's from this point onwards. I shouldn't say Delhi. Delhi is on the Yamuna. Yeah, ulta bol diya. Nizamuddin Bridge is, let's see, downstream of Agra, I think. Yeah. Yeah. No, wait a second. No, that's also wrong. I've forgotten where it's located. Um, it's between, no, I think there's some mistake over here. Anyway, so it's in that area, but this is Ganga, not Yamuna. Yeah. So anyway, the DO levels are not class A. Okay. So the whole point over here is to give you an idea of the polluted stretches of the river. So you can do this exercise for any river in the country or anywhere else in the world. So, you can get an idea of which stretch of the river is good quality water and which stretch of the river is poor quality water. So based on these two parameters of BOD and DO. Um, the reason for putting this table over here is solubility of oxygen. In the last class, I already mentioned that the dissolved oxygen saturation concentration is a function of two parameters. One is temperature and the other is salinity. So here, salinity is shown in terms of chloride concentration. So as the salinity increases, the DO level for a given temperature decreases, and as the temperature increases, so does the DO. This is DO saturation level at 1 atmosphere pressure. So this is the main point to remember. You can see the range at 0 salinity, 0 degree centigrade temperature, the DO level, saturation level is 14.62 milligrams per liter. At the other end, and it goes further down, if your salinity is higher or your temperature is higher, then the DO level, the DO saturation level will go even further down. There are empirical equations that can be used to approximate this kind of data. We'll come to the problems later at the end of the class. After I finish the theory part, then we will revisit all these problems and then I'll give you some time to solve them if we have time. Yeah. Next point is the way to calculate what we call the dissolved oxygen sag curve. Now, I've already mentioned to you in the previous class and in this class that supposing you have a river and you have a single point discharge of wastewater. How is the dissolved oxygen level in that river going to be affected by this wastewater discharge? So here is our river. We're using what is called a plug flow model. If you don't know what a plug flow model is, don't worry about it. The only thing you need to remember is that in a plug flow model, there is no mixing. So just make a note of it. Plug flow implies there is no mixing in the direction of flow. So if you look at this gray box, the gray box shows you that there is mixing, complete mixing in the direction perpendicular to the flow of the river, and in the direction of flow there is no mixing. So this is zero mixing, and it makes it simpler. It's just a way of making certain assumptions to make the calculation simpler. Okay. This is a very old model. It's been close to 100 years now. 1925 is when this report was published. It's called the Streeter-Phelps DO-SAG curve. And I think the data they collected was exactly 100 years ago. So it's been validated any number of times in most locations. So this is our plug flow model. We also make the assumption that the river water velocity is constant. So our point zero in terms of either distance or time is the point at which the wastewater falls into the river, and the river is fresh water. So there is a particular flow rate in terms of cubic meters per second, that is QR, and QW is the flow rate of the wastewater. So this is a single point wastewater discharge model. This is a problem that tells you how to do the mass balance. We will, like I said, do this at the end of the class. We'll come back to this point. So let's go through the derivation of what we call the dissolved oxygen sag curve. And like I said, it's also called the Streeter-Phelps model. Now, at the point at which the water is falling, that is the point that we are calling x is equal to 0 and t is equal to 0. Now, the river is fresh water, but it may have some amount of organic matter in it. So the water in the river to begin with at t is equal to 0. Let's stick to t. At t is equal to 0, there is a certain amount of initial deficit. So DO saturation for that temperature and salinity condition is already going to cause some deficit as, let me rephrase that. For the temperature and salinity in the water at that point, at x is equal to 0, t is equal to 0, at that point, you will have a certain DO saturation value. Now, the water also has some organic matter, and that organic matter is going to cause the DO level to be less than saturation. Very rare. It's extremely rare to find a water sample that is exactly at DO saturation. Unless it's really pure, really clean water, it will not be at DO saturation. So let's assume that when the wastewater falls, there is already some deficit. And this deficit is the difference between DO saturation versus the DO in the water at that point. So DOS minus the DO in the river water sample. That is our initial deficit, D0. So D0 corresponds to X0 or T0. That is the first point. Now, this wastewater is dumping organic matter into the river. It's untreated. Let's assume it's untreated and it's highly biodegradable matter. So there is some BOD associated with it and it will exert an oxygen demand. This is all that we have seen in the last class. Now, how do we do the analysis, the mathematical part of it? Okay. So the first thing we want to do is we want to know how is the rate of change of deficit happening. So this capital D is the deficit. And like I said, the deficit is DOS minus, right here, DOS minus D. D at any point, which is some point less than DOS. And so this is, again, let me put it in another way. You can also write it as D is equal to DOS minus the DO in the river water sample. Okay. Now this D is the driving force. If there is no deficit, there is no driving force for DO from the air to come into the water. Okay. And remember that oxygen is poorly soluble in water. It does not react with water. It remains in molecular oxygen form, and it is very, very sparingly soluble in water. So rate of change of deficit is small d capital D divided by dt. So this is the rate of change of deficit. This rate of change of deficit is going to be dependent on two processes. Let's take a look at both those processes. Two things are happening in the river at any given point in time. Because there is organic matter, this organic matter is biodegradable and it exerts an oxygen demand. So the bacteria, let's assume that the bulk of the species are bacterial species. They are going to utilize the organic matter, convert it to CO2 and water, and in the process they are going to utilize oxygen. So that is what we call the process of deoxygenation, and we have seen deoxygenation in the BOD test. So when we do a BOD test in the lab, what we are doing is we are measuring the rate of deoxygenation over a 5-day period. So this is the rate of deoxygenation. Okay, now as long as there is a deficit, just like any concentration gradient, it's going to be a driving force. So this driving force will bring oxygen from the atmosphere into the water as long as the DO level in the water is below DO saturation. Okay, so that is our driving force, and that driving force will result in re-aeration. So if the DO of the sample is below DO saturation, oxygen from the atmosphere will enter water. So we have two processes, rate of deoxygenation minus rate of oxygenation or re-aeration. Depending on which textbook you use, both these words are acceptable, oxygenation or re-aeration. Now, rate of deoxygenation is basically based on the derivation we did in the last class about the BOD test. Just to refresh your memory, I'll just show you those graphs so that you get your right here. So if you know, we did all this derivation was done for the BOD T. So this is the oxygen demand remaining at any point T. So we're going to be using these equations in our DO. So the first equation, which is the rate of deoxygenation, Kd is our rate constant, L0 is the ultimate carbonaceous BOD, yes, again, yes. So we abbreviate that as carbonaceous BOD, CBOD, okay. And you may want to include nitrogenous BOD or not, but we normally base it on ultimate carbonaceous BOD. It can include, yes, it can include, you can play with that idea, you can add nitrogenous BOD as well. So anyway, Kd, L0, and this is the rate at which this carbonaceous BOD is going to be utilized by microbes. Now, the reason we are focusing on carbonaceous BOD, this rate constant applies only to carbonaceous BOD. If we take total BOD, which includes nitrogenous BOD, then the Kd value will be different. So you will have Kd1 and Kd2. Kd1 will be for carbonaceous BOD and Kd2 will be for nitrogenous BOD. Okay, so that can be done, but that's a further complication. Let's not get too complicated here. We will stick to carbonaceous BOD. So Kd L0 e to the power minus Kd T. That is the rate at which L0 is being consumed. Okay, and then, like I said, rate of oxygenation is directly proportionate to the deficit. And if you remember how concentration gradient of any type is a driving force, so the same concentration gradient is a driving force right here. This driving force can be rewritten. So we can write the deficit can be rewritten. So this is the initial deficit. Remember, it's a first order reaction. We are assuming it's a first order reaction. D0 e to the power minus K O, O for oxygenation, not zero, Ko for oxygenation or reaeration times T, T being the same for both of them. Um, so that takes care of the whole thing. And now you can substitute this equation into the one over here for the deficit. So deficit is DOS minus DO at any time T, and DOT or DO at any time T can be written in the same form. So you just plug in this equation and you get the actual Streeter-Phelps oxygen sag equation. Okay, so this is what the Streeter-Phelps oxygen sag curve looks like. So you have your initial deficit over a period of time. Let's start at the beginning. When the organic matter is very high, what will happen? This organic matter will be consumed by the bacteria. They will also consume oxygen in the process. So the rate at which deoxygenation is happening is rapid. So deoxygenation for the first phase is far faster than reaeration. So let's take a look at the first phase. So in the first phase, rate of deoxygenation is very high. Because there is a deficit, the rate of reaeration is also high. So it will bring the oxygen. So your rate of reaeration is opposite of the deoxygenation. Deoxygenation brings DO down, aeration brings DO up, and the two will determine the DO level. So because in the initial period, organic matter is high, oxygen is being consumed as rapidly as possible. So you get a immediate deficit. There comes a point when the two are equal. So that is the critical point. When the rate, see the crossover, when the two intersect, at that point, you know from your calculus that that is the critical point. That's the minima of the curve when the slope of this curve is zero. So this is the minima, and at this point oxygenation equals deoxygenation. So we call it critical point. So this critical point Xc is equal to Xc is not equal to Tc. The same point corresponds to critical point in terms of distance or time. Because the driving force is the deosaturation level, after the critical point, the rate of reaeration is now higher than the rate of deoxygenation. So the DO level starts coming back up. So let me see, yes. So the DO level starts climbing, and eventually, if there are no further wastewater discharges, it will eventually reach DO saturation. And this entire phenomenon is called the self-purification capacity of the river, provided there is no further discharge of wastewater. Now let's come to how do we find the critical point. Now, if I am trying to manage, let's say my job is to manage the water quality in a particular river. It can be Ganga, Yamuna, or a smaller river. Okay. We know that the velocity in the river is related as x by t. So you can write your equation into assuming that the stream has a constant cross-sectional area. Now the interesting thing in nature is that no stream has a constant cross-sectional area. So these velocities themselves are actually varying in nature. But for the sake of simplicity, we are saying that we're going to assume it's a constant cross-sectional area. This above equation, the one that we derived over here, 3.5.4, will get modified. You can write it in terms of distance and velocity. Now, distance is measurable easily, and so is the flow velocity of water in the river. So these parameters are easily measured. They can be plugged into that equation, and you get the new equation. Now, I've already mentioned what is critical time. Critical time is when the stream condition no doubt is the worst, but mathematically speaking, it is the time at which rate of deoxygenation is equal to rate of aeration. And I will ask you to refer to the text for this matter. You can refer to either master's text or to mine. Either way, you can do the derivation because you can simply equate these two processes. So dd by dt is equal to 0, which means rate of deoxygenation is equal to rate of oxygenation, and you calculate for Tc. Tc is the time at which the two are equal. Okay, so again, like I said, I'm not going to go into the mathematical details of it. I'm going to leave it for you to do the derivation with pen and paper. And this is important because you know how to do it. So I'll leave it at that. And this is your final equation. So you have a solution to compare your work with. Okay, now what are the factors that affect the DO-sag curve? The DO-sag curve itself is going to change depending on several factors. Let's stick to single point source. The first thing is temperature. We know that K value, the reaction rate constant, is most affected by temperature. So let's see what happens at different temperatures. So 20 degree, 30 degree, 40 degree. This is the DO curve as the temperature changes. So we know that as the temperature increases, the KD value increases. Now, if the KD value increases, then that critical point at which the the slope of the curve is changing from 0 to it goes in the opposite direction. So you can see that this critical point for 20 degrees is around 20 miles in this particular graph, and at 40 degrees it's around 10 miles. Okay, so this, because everything is happening at a higher rate, all your reactions, deoxygenation as well as oxygenation, both are happening at a higher rate. So the critical point is achieved at a much closer distance to the source. Okay, so this is our wastewater source, and the distance from the source to the critical point becomes smaller. That is one thing. So during summer, so summer and winter, in summer, the water temperature will be higher compared to winter. And because of the change in temperature, you will get critical point at a much sooner point rather than in summer rather than in winter. So the first two are related to each other. There's another factor which I haven't mentioned here in this slide is the monsoon effect. Now in monsoon, what happens is you get a huge flush of water from the land area. And this is basically non-point sources. Now, depending on the nature of the surface runoff, if it is an urban area, if it is highly polluted, then the organic loading into the river can be very high. If, on the other hand, you have irrigated land or even forest, then the flush that comes with the monsoon is not going to bring too much organic matter with it. So it all depends on conditions. That is also another huge factor because the river will be diluted. The water in the river will be diluted enormously, but it also depends on the organic loading that comes along with the water. It's a major factor. Then we come to effect of photosynthesis. Now, in this water, in the river water, you have several photosynthetic organisms. You have algae, you have aquatic plants, and all of them are adding DO into the water during the daytime. And there is a small amount of consumption of DO during the night due to respiration. So this will result sometimes in very anomalous readings in water. Sometimes people have found that the water sample is super saturated with DO, and that is mainly because of photosynthetic organisms like algae and aquatic plants. Then we come to nitrification. I've already mentioned to you that we have carbonaceous BOD and nitrogenous BOD. Now, this nitrogenous BOD is associated with the nitrification process. So here we have organic nitrogen and ammonia being converted to nitrite and nitrate. So it is possible that because of this nitrification process, you may see a secondary dip in the DO-sag curve downstream from the initial critical point. It's never going to be as bad as the carbonaceous POD. Remember, nitrogenous POD is much slower in the sense that the KD value associated with nitrification is going to be much, much less compared to carbonaceous BOD. I've already mentioned that waste concentration is another major factor. So if you have high amounts of organic loading, which means waste concentration is much higher. When that is much higher, the amount of DO consumed will also be higher. And because of that, again, you will get critical point at a much sooner uh, uh, time point or distance point compared to another case. So this is what you might expect. So let's say I have a treated wastewater discharge versus an untreated wastewater discharge. If I have an untreated wastewater discharge, I will likely get zero oxygen in some parts of the river. That will be completely anaerobic. Then there are unhealthy levels. So we know from the use-based classification, we know that there is a minimum acceptable DO level. So that is considered unhealthy, and below that it's all anaerobic. And anaerobic is very easy to inspect. If it stinks, if the river water stinks, it means it's already anaerobic. It means there isn't enough oxygen, and the gases of ammonia and hydrogen sulfide, which come from the biodegradation process, all of them are fairly high, and that means it's already very unhealthy. Then we come to the recovery point, and this is the self-purification part of the curve. So as long as the loading of organics to the river is not very high, the river will recover naturally and it will purify itself. And that's why for thousands of years, people have been able to throw wastewater into the river and the rivers purify themselves. And that's why they are acceptable to people and so on. But what has happened in the last few hundred years is that the population pressure has increased. The amount of wastewater that is being discharged into the river is increasing, and we are no longer giving the river any time, because time and distance is what the river needs to purify itself. And if insufficient time or distance are not given, then the river never achieves saturation again. Okay, so this is all about the self-purification capacity of any river, and this applies to any river. Any questions at this point before I move to the next point? No questions? All right, so yes, was there something? No? Okay. So let's come. So right up to this point, I've been talking about water quality in flowing water bodies. Let us now look at water quality in standing water bodies. So we have two parameters over here, light and water, and how light in water and how it gets attenuated in water. So we're going to look at certain issues. So first issue is wavelength, second is depth, and third is the presence of light absorbing substances. Let's take a look at the depth profile. Now, most of you have done at least that much observation in your life. If you look at a certain lake or a pond, what do you see? Sometimes you can see up to a few centimeters deep. Sometimes you can see maybe a 1 foot, 2 foot, 2 feet, or even deeper. And sometimes it's very difficult to see what the depth of the water is, right? So we have an instinctive understanding that the ability of light to penetrate into the depth of the water column. We call this water column. So when you're staring into a water body, whether it's a well or a lake or a pond, we call that the water column. And you know that if you say that the light that is incident at the surface is 100%, relative to that, if you are able to measure the light at different depths in the water column, then you can kind of create a depth profile, the one similar to what is shown over here. I'll just give you an example of something. It's called a Secchi disk. A Secchi disk is, the spelling is SECCHI. Okay, so Secchi disk, it's a white disk at the end of a long rod, and that the length of the rod may be about uh, 5 to 10 feet or even longer. And what is done is this white disc is dipped into the water, and the depth, the rod itself has markings. So 1 foot markings are there on the rod, and you dip it until you cannot see the disc anymore. So that becomes the point at which zero light is penetrating, because if you can't see it anymore, it means light does not penetrate to that point. Okay, so that's how simple the Secchi disk was for understanding the attenuation of light in the water column. And so you have two cases shown over here. There's a clear water, clear river, again, clear lake, and then we have a turbid lake. So in a turbid lake, zero light is entering at around 5 meters, and in a clear lake it goes as far down as 20 meters. It's hard to imagine because most of the lakes in our country don't have that kind of clarity at 20 meters. It's very hard to imagine, but there are highland lakes and so on that do have this kind of clarity. Now, if you were to plot this graph and then take the first order constant, so you would get what is called the vertical extinction coefficient or the attenuation coefficient. So this is not a rate constant, it's just a depth extinction coefficient, yes. And K is equal to 0.2 per meter. This should be small m. So 0.2 per meter and 0.9 per meter for a turbid lake. So you can see the attenuation of light is, this is not a time unit, it's a distance unit. Okay, now we come to light attenuation and the measurement of it. Now in the lab, and perhaps you have done this in school as well, you probably know that you can measure the concentration of any substance if it is added in water. So you have, let's say, a single compound added to water, and you take various samples and you gradually increase the concentration of the samples. And then if you measure the light being either absorbed or transmitted through that sample, then you will find that as the concentration increases, the amount of light absorbed by that particular compound will increase. Okay, so I and I0 are the light intensity entering and leaving the solution, and C is the concentration in the sample. So K is our proportionality constant, and uh, that is also the attenuation coefficient. So if the light path, the distance that the light has to travel, in general we use a spectrophotometer, and in a spectrophotometer the cell size is fixed. So the path length is fixed, which means it's normally 1 centimeter. So for a 1 centimeter path length and different concentrations, we can find the concentration of any particular substance. We can calibrate the instrument and we can fix a particular wavelength. I'll come back to this issue of wavelength in a little bit. But the first point is concentration. Okay. The second point is depth of let me put it another way, the length of the light path. I've already mentioned that in the second case, all this here, the length of the light path is fixed and the concentration changes. In the first case, we fix the concentration and change the length of the light path. So let's say we have, just like the Secchi disk example, if I change the depth to which I can see light, then um, I'm varying the depth of the water through which light is passing. So here we have I by I0, which is transmittance, and you can write it for a particular concentration. So let's assume that the lake is a complete mixed reactor type phenomenon. Again, for those of you who are not familiar with these words, let's assume it's completely mixed. So whether it's 1 meter from the surface or 10 meters from the surface, if I assume that the concentration of particulate and organic matter is the same, and then I take these Secchi disk type measurements, then I should be able to come up with something like this. Okay, so I by I0 times e to the power minus kd is the Lambert's law of light absorption. And then Beer's law is what I already explained to you. And that is what we do in the lab. We use either a spectrophotometer or a turbidity meter or turbidity meter or a nephelometer. So these are different types of instruments that are used for determining how much light passes through the sample cell. So we have a cell. It's a very small cell. It's about 5 centimeters long, 1 centimeter wide, and light is passed through it. So whether you're measuring absorption or transmittance, either way, you can get this kind of result. Now, the combination of Beer-Lambert's law, where you combine concentration and depth of the light path or the length of the light path, however you want to see it, you can write it in terms of transmittance. Transmittance is I by I0. I0 is the intensity before it enters the water sample, and I is the intensity after it passes through the light sample. And this is exponent e to the power minus k dash. K dash is to keep it separate from the first k and the second k. And so you get minus k dash c times d. This is not a simple summation of Beer and Lambert's law. It takes quite a complicated derivation to arrive at this point. I'm not going to go into that. I'll leave it to you. For those of you who are interested, do it on your own. And light absorbance is the reciprocal of transmittance, and you get this kind of, yeah, so that's it. So absorption is the natural log of the reciprocal, so you get this. So I think I've covered two of these points, depth and light absorbing substances. Now the light absorbing substances can be dissolved substances, they can be suspended solids, and they can be plankton. Plankton are suspended solids. Plankton are algae cells, diatoms. All these are examples of living organisms which are measured in terms of suspended solids. So these are all the things that are present in the water that will absorb light. Now let's come to the third one, which is wavelength. Before we go to wavelength, this is an example of the difference between different types of water. This is ocean water. I've been talking about lake water. This is an example of ocean water. So here we have coastal water. You can see it's green and ocean water is blue. And you would say, why is that, right? So green is because of plankton. Plankton, most of it is algae. Algae are photosynthetic microorganisms, and they have chlorophyll in them. So that's what gives them a green color. So the coastal waters, where you have very high nutrient concentration, especially nitrogen and phosphorus are very high in the coastal regions because of wastewater discharges. And this is what you get in these areas. Now, in terms of ocean waters are very, very poor in terms of nutrients. Nitrogen and phosphorus tend to be more or less constant. Planktonic growth is very poor. Remember what I showed you in the ecology class? I said to you that the ocean, the open ocean is more or less like a desert in terms of biodiversity. It has very poor biodiversity. It has very low levels of growth, or NPP, net primary productivity. So I've shown you all that. So because of that, the water is very clear. So that's why, and we'll come to why is the water blue. Let's take a look at that. So here is the absorption spectra for pure water. So here you, let's say you can do this in the lab. Any one of you who has access to a spectrophotometer, I've done it, so I can confirm that. You can, any good spectrophotometer will allow you to do absorption spectra for pure water. And when you do that, you can go through the entire spectrum all the way from, let's say, 180 nanometers all the way to 15, this is about 1200 nanometers. Okay, these are different absorption spectra for pure water as published by several researchers. The y-axis is a log scale, the x-axis is a linear scale. What does this show us? This shows us something. Look at the color scale at the bottom. Where is the absorption of different parts of the visible spectra? Where is it least? So the least absorption coefficient is in the blue region. This is the blue region where you get the minimal amount of absorption. So blue light is not being absorbed by water. All other wavelengths are being absorbed by water. That's why it looks blue. So this is, and you can't measure it at small path lengths. You need hundreds of meters of clear water, which happens only in the deep ocean. So it's only in the deep ocean that you will be able to realize this kind of phenomenon. And this phenomenon is related to this absorption spectra. So it's in the blue region that you can see it over here. So 455 to 500. So it's right bang over here in the middle. And so it's the minima, and that means blue light is least absorbed, and that's why water looks blue. Absorption means you can't see it, because any time light is absorbed, it means you can't see it. It's only what is reflected that you can see. So we come to the next point. So even in Cormandy's text, this is actually data from his textbook. And what you see over here is the profile for different colors which are related to different wavelengths. So here is the relationship between different colors of the visible spectra and their relationship with different wavelengths. So you can see that as the depth of water increases, the least absorption is for blue light. Red light is absorbed first, orange second, yellow third, violet fourth, green fifth, and the last one is blue. Okay, so the same information is being provided in a different way, and the same point that blue light is absorbed to the least extent compared to all the other colors. What difference does that make for us? I wanted to remind you of this point. Okay, so green versus blue. Green is absorbed over here. Now, I should also mention to you, I think I mentioned it when I was talking to you about NPP in the ecology topic. I said I showed you some ocean photographs. So I showed you satellite images where I said that you can measure chlorophyll concentration in water simply because of the color that is reflected. So this is an example of that, that coastal waters have high nutrient concentration. Because of that, they have high planktonic growth, and because of that, the planktonic growth will give you high chlorophyll concentration, and that high chlorophyll concentration will give it a green color. Okay, so these are all the points that I wanted to cover, and if you have any questions, ask. This is a good point at which you can interrupt me and ask me if you have any questions. Before we move to the next point. No questions? Okay, in that case, we start with the next point, and that is again another phenomenon that is observed in standing water bodies. So, something that again all of you must have observed very often when you look at small lakes and ponds, you see that there is a green layer at the top. This green layer is a layer of algal growth, and these algae are called phytoplankton. So all these small photosynthetic microorganisms, that's algae, and that is going to collectively it's called phytoplankton. So excessive growth of phytoplankton and aquatic plants is often observed on the surface of standing water bodies. Now we come to uh, why is it that these microorganisms are growing at the surface of these water bodies? So the main reason is high nutrient concentration. And because of this excessive growth, um, there are three words that we use: oligotrophic, mesotrophic, and eutrophic. So eutrophication is something that happens naturally. It is a natural aging process, and all lakes and reservoirs undergo this process. So you get this excessive growth of phytoplankton and plants because of high nutrient concentrations. And in the ecology topic, I said to you, I will cover the law of the minimum. I will be covering that over here. It belongs in both cases, it belongs in both topics. So in either case, we will need to cover it. Okay, so like I said, it's a natural process, and it causes a lot of degradation of the natural water quality of any standing water body. When pollution exacerbates this process, when it accelerates this process, this is a natural process which can get accelerated because of human activity. So if I discharge wastewater, wastewater contains carbon, but it also contains high levels of nitrogen, phosphorus, sulfur, and so on. So, because of the high input of pollutants like these wrong again, macro and micronutrients will contribute to what is called cultural eutrophication. So, cultural eutrophication is accelerated eutrophication of these water bodies. And these water bodies, like I said, the water quality goes down, and because of cultural eutrophication, the degradation in water quality is very, very fast. So all lakes will accumulate silt and organic matter. The nutrient level will increase. Remember, there's no output. How does a standing water body differ from a flowing water body? A flowing water body has input and output. A standing water body has input but no output. The only output of water is generally by evaporation. So that results in accumulation of silt and organic matter. It will also result in an increase in nutrient levels. These nutrient levels will remember the primary productivity. So you will get higher productivity at the uh, bottom of the trophic pyramid. So phytoplankton will grow extremely rapidly. And because they are growing so rapidly, eventually they will die, they will decompose, they will fall to the bottom, and you will get high amount of sediment and organic matter at the bottom as well. So the sediment in these lakes, ponds and reservoirs will increase over time, and it will also result in turbidity in the water because of microbial growth, both of algae as well as bacteria. So all these microorganisms will contribute to an increase in turbidity, to an increase in silt and organic matter and nutrient level. So the whole thing just continues forever, and it's sort of the nutrients within the standing water body will be constantly recycled because they are essential for phytoplankton growth. And remember that the source of carbon is carbon dioxide from the atmosphere. So the cycle continues within the standing water body. Oligotrophic lakes. As I said to you that these kinds of lakes, the one I started with right here, this kind of clear lake, which is very hard to imagine in urban settings because urban areas are generally prone to a huge amount of pollution. So where the water is clear up to 20 meters is unimaginable in these urban settings. But perhaps in the Himalayas and perhaps in other higher latitudes and higher elevations, you may have oligotrophic lakes. So the alpine lakes, the Himalayan lakes, to some extent, many of them are considered oligotrophic if they are not polluted. And they have very, very low nutrient levels, and therefore the clarity of the water for tens of meters is very, very high. So low nutrient levels will give low primary productivity. And that's what you want, when people go for mineral water from these kinds of lakes, that's because they are oligotrophic lakes. They have very low levels of microbes, very low levels of nutrients, no smell, no taste. It's genuine, clear water, of natural origin. So what are the water quality impacts that are associated with eutrophication? The first is noxious algal growth. So like I said, eutrophication itself means noxious algal growth. And this leads to an increase in that green layer. That green layer is what we call scum. Algae, as microorganisms, they exude or excrete certain toxic compounds. So if you happen to be using this water for drinking purposes, even if you filter the algal cells out of it, you may still get a stomach upset, even though you disinfect the water and so on. And that's because of the toxicity associated with these exudates. If you get a smell, or if the water has some color, either yellowish or greenish, it's all because of these algal cells. So toxicity, color, taste and odor, turbidity, and natural organic matter. Now, another point to remember is that, let's say in the summer, especially in let's say hilly environments where you have lakes at high elevations, they are pretty good quality, let's say in winter. And then when summer comes, temperature starts increasing. You get algal growth because of some amount of nutrient input to these lakes. What will happen is they are contributing to natural organic matter. NOM stands for natural organic matter. And that is the total amount of organic carbon in the system. We measure it in terms of TOC, total organic carbon. Now, when you disinfect this water in the summer, because the NOM level is higher, so the amount of chlorine required to achieve the same residual is also going to be higher, and you're going to get disinfection byproduct formation, which will again be higher because everything else is higher. So this is the chain of reactions that will happen because of algal growth. So the water quality, like I said, comes down because of these microorganisms. Then we create an anaerobic zone below the algal layer. Now, I don't have my sketches over here. I normally do this on a blackboard. But if you can imagine it, that you have a lake system. I don't have a sketch over here. I'll add it later. But just imagine a lake and you have a layer of algae at the top. Now this layer of algae is absorbing sunlight and CO2 from the atmosphere. What happens to the water below that algal layer? That layer below the algal layer is going to get a small amount of oxygen, which is going to be consumed by the bacteria that are in the lower layers. So bacterial growth and organic decomposition will happen in the water below the algal layer. So because of this organic decomposition, pH will fall. Acids are generated in decomposition. pH will fall and so will the DO levels. Just remember the glucose equation. Just imagine NOM is glucose. That's what NOM is for these bacteria. Okay. So these bacteria are utilizing organic matter. Just remember, glucose plus oxygen is going to CO2 and water. So CO2 in water is acidic and that will bring the pH down. That is one part of the point. The second point is that the process of organic decomposition releases acids. So acids are generated in the decomposition process. So both points are correct, that carbon dioxide will lead to the formation of carbonic acid and organic acids of low carbon amounts. So you have C1, C2, C3, C4, these kinds of, so you have formic acid, acetic acid, propionic acid, butyric acid. All these are acids that are generated when NOM is utilized by bacteria and DO is consumed. So these two things will happen together. Low pH, low DO levels will happen because of bacterial growth in the layers below the algal layer. Now remember, algal growth is providing some amount of dissolved oxygen. Then we come to, if the DO level drops, what will happen? The fish that are growing in those lower layers will perhaps be, it will be difficult for those fish to survive. So there will be loss of habitat for fish, and those people who depend for their livelihood as well as for their food on these fish will also lose. Now, these same nutrients which contribute to eutrophication and the growth of algae are also going to contribute to the growth of weeds. So this excessive growth of weeds, and you have probably seen it like water hyacinth and so many other aquatic plants, you can see in these water bodies, you not only have a scum layer at the top, but you also have a whole bunch of weeds that are growing in this water, and they result in loss of open water. So if it is a recreational area where you have people either swimming and boating and so on, so those kinds of activities will be inhibited because of this growth of aquatic plants. Now, this excessive organic matter decomposition will result in a huge amount of sediment because of the death of both algal as well as bacterial cells. So eggs and bugs and so many other larvae producing organisms, all of them that have sediment as part of their life cycles, those eggs and larvae will be smothered by organic matter, and that will result in disturbance of the aquatic ecosystems. Then we have cyanobacteria, which are also algae. They're actually bacteria, but they're photosynthetic, let's call them photosynthetic bacteria. Some of them are inedible by zooplankton. So these zooplankton are the small organisms. Some of them are not visible to the eye, but some of them are. These are the organisms that feed on phytoplankton. Okay, so some of the zooplankton find it difficult to eat these cyanobacteria if they happen to be toxic. That is one effect. And some of the algae are actually toxic, as I mentioned in the first point. Okay, so you have several toxic effects that are related to the growth of algae. It depends on the species. Some of them are more toxic than others. And I normally give the example of red tide, which is something that happens in the ocean water. So it's not so much related to eutrophication. It can be, yeah. So you can get eutrophication of ocean waters as well, but that results in what are called red tides. And these red tides are the growth of red colored algae. And these red colored algae, they literally bloom in a very short period of time, maybe even overnight, and they turn the color of the water changes to a blood red color. It's a bright blood red color. It's very shocking. And there are photos on the internet. You can do it, just search for it and you'll find them. The problem with these red algae is that they are neurotoxic. They exude these exudates of this red algae. They are neurotoxins. So people who have gone swimming in these waters, which have turned red because of the growth of red algae, they have either fainted or died of suffocation. And these are all examples of the toxic effects of algal blooms. Now, because you have excessive organic matter even in the sediment in these lakes and reservoirs, there is a lot of toxic gases that come out. So you have ammonia, hydrogen sulfide that are coming out of the sediment as it gets degraded, as the organic matter gets degraded. So you have this phenomenon, which again leads to loss of aquatic habitat for fish and other organisms. I've said all this about excessive nutrient levels. Now let's take a look at what is excessive. How do we define excessive? And when do we say that a particular nutrient is the limiting nutrient? This is a very, very important point from every point of view. If you are thinking in terms of biology, the law of the minimum is a fundamental principle that is extremely essential to our understanding of what happens to the growth of any organism, not just microorganisms, but even higher organisms. Okay. So, like I said, this is a fundamental principle that is applicable to the growth of all living organisms. It comes to us from agricultural science as far back as 1828. What does it say? It says that any element that is least available relative to the requirements of an organism is defined as the limiting nutrient. Now, the growth of the organism is going to be proportionate to the concentration of this limiting nutrient. So let's take a simple example. Bacteria, we use an empirical formula C5H7O2N. Please write it down. C5H7O2N. That is a simple empirical formula for a bacterial cell. Now, if I ask you, what is the limiting nutrient for this bacteria? You cannot answer it offhand. You know, only looking at this formula, you know what is the proportion of carbon, hydrogen, oxygen, and nitrogen that the bacteria need. So based on this formula, you get an at a glance information. So C5 means 5 moles of carbon are required for every mole of nitrogen. So immediately I know that the ratio of carbon to nitrogen on a molar basis is 5. And then you can convert it to milligrams and grams. So depending on the actual concentration of carbon and nitrogen in any water sample, I can then analyze it, compare it to the required ratio. So the relative requirement is 5:1 on a molar basis. And depending on what I have in my water, I can say either carbon is limiting or nitrogen is limiting. Okay, so this is how we apply this particular law to water, and to figure out whether nitrogen is limiting or carbon. In general, any one of what I call the big six can be a limiting nutrient. The fact of the matter is, any element that is required for the growth of an organism is, from a strictly theoretical point of view, any element can be the limiting nutrient. And very often we talk about nutrient deficiencies, right? So nutrient deficiencies, as you know, happen only due to the absence of certain trace elements. The same thing applies to human beings as well as bacteria. Principle remains the same. Plants, bacteria, algae, human beings, everyone fits over here. Okay, all living organisms have to deal with this. For practical purposes, we use one of the big six. What are the big six? CHONPS. Okay, so we generally restrict ourselves to these six. But that does not mean we do it for simplicity reasons, not because the big six are important, not at all. In general, the growth of any organism is limited by what we call micronutrients, not the macronutrients. But our ability to measure macronutrients is much higher than our ability to measure micronutrients. So what we do is always simplifying matters. Nature is not simple, we are. So, like I said, I'll do this and let's see how much. Yeah, we'll finish this and then we'll stop and we'll do some problem solving. Okay, so here you have a reaction for the conversion of CO2, nitrate, phosphate, water, and protons, and their conversion into an algal cell. So the product of this reaction is 1 mole of algae and 106 moles of CO2, 16 moles of nitrate, 1 mole of phosphate, 122 moles of water, and 18 moles of protons are utilized in the process. Now, if you look at the empirical formula, this is an empirical formula for algae. I've already given you an example of the empirical formula for bacteria. It's a broad generalization, and different species, if you measure them in the lab, you'll get small changes, not big changes. They are all within a certain, you can see the graph. 16 moles of nitrogen are required by algae for every mole of phosphorus. So N by P on a molar basis is 16. And on a weight basis, you simply multiply it by the molecular weight and you get 7.2. This is what we call the Redfield ratio. Redfield is the name of the person who came up with, he happened to have traveled all over the world and took samples, water samples from all the oceans of the world. So he had samples from Atlantic, Pacific, Indian Ocean, and all these things. And what he found was amazing, that the ratio of carbon, nitrogen, and phosphorus, no matter where you are, remains more or less the same. So there was very little difference. You can see the data over here, that the data are, and this is another example of how there is a steady recycling of nutrients in nature. So you can see uptake and release. So these nutrients are taken up by phytoplankton and they are released by phytoplankton. And that's how the biogeochemical cycles in nature continue, and they remain in equilibrium, they remain in steady state. So you can see it all fits within a very tight band, and the ratio is constant for the entire planet in natural conditions. So any disturbance of this ratio indicates that it's most probably an anthropogenic activity that's causing change in those ratios. So this is called the Redfield ratio. Now, if you put it like I said, in C is to N, you can compare two elements or you can compare all three. So I've given you all ratios. C is to N is to P. So 106 is to 16 is to 1 on a molar basis. And when you do it on a weight basis, it's 41 is to 7.2 is to 1. And C is to N less than 5 means carbon is limiting. Now, when I say C is to N less than 5 means for every wait a second. Right. So for C is to N, I want minimum, let's say 6 or more. And if it's less than 5, I can safely say that carbon is the limiting nutrient. If it is higher, it means nitrogen is limiting. So the phytoplankton or algae are going to grow in proportionate to whatever is the limiting nutrient because they cannot exceed that. That is the ceiling. That is the maximum. At N is to P less than 7, nitrogen is limiting. At N is to P greater than 7, phosphorus is limiting. I think I have said everything over here. Yeah, okay. So we're going to stop at this point and go back and solve some problems. Okay. If you have any questions, now is a good time to ask. Otherwise, we start solving some problems. I gave you this problem already. Yeah, so THOD for C6 compounds. I hope some of you have done it. All of you have done it. You can turn your mic on and tell me whether you've done it or not. If you had any problems, ask. Okay, let's now come to a BOD problem. So our wastewater has a BOD 5 of 300 milligrams per liter and a reaction rate of 0.2 per day. It's a first order reaction rate constant. The total gel-dal nitrogen is 40 milligrams per liter. You have to find out the ultimate carbonaceous oxygen demand, the ultimate nitrogenous oxygen demand, and the remaining after 5 days. So if I revisit this graph, yeah, so this is at 5 days. What is remaining after that? So there's a lot more that's there, and you have to tell me what is remaining. Okay, so let me give you 5 minutes and you should come up with the answers. The answers are already there, and you should also be able to draw the concentration profiles. Let's say in a test or exam, I give you this question. You should be able to draw profiles just like these. So these are the profiles that I expect from you, both for DO as well as the nitrogen species. Some understanding of what is going on. I won't ask you multiple processes, multiple point discharges. It's too complicated. So take 5 minutes and tell me if you get the same answers. Are you all trying it?
Yes, ma'am.
Okay, keep going. If you solve it, just raise your hand so that I get an idea who is solving it at what pace. These are going to be on the test, so whatever you tell me is going to be very important.
Ma'am, both of these are different, like the ultimate and the after 5 days.
That's correct. That's correct, yes. Just remember this graph. Do you remember this graph? So BOD5 that we measure in the lab is shown over here. And the ultimate carbonaceous BOD is the line above that. So it's a small fraction that you are measuring in the lab. And what is remaining is, so L0 is basically BOD5 plus whatever is remaining. So this is it. Just think of it in terms of organic matter rather than DO. Even though we measure it in terms of DO, think of it as a surrogate for organic matter. Instead of writing BOD, if I write CT, it won't cause so much confusion. I'll keep this open if you need it. Any answers? Please raise your hand if you have finished. The answers are on the screen. I need to know whether you need 5 minutes or 10 minutes to solve this problem.
Ma'am, can you go back to the question?
Can you see it? You want the problem? Yeah. You can confirm your answer. The answers are on the slide. Please raise your hands if you have finished. All right, good. That's one. Can we move to the next problem? Okay, there are some slightly more complicated problems. I won't go through them. They're all based on the same equation. Let's tackle another one. This one is again, I won't say it's a complicated problem, but you need to draw a sketch for it. So please go through it and ask me any questions if you are unable to understand it. It's a fair, make a sketch. There is a water with two wastewater discharges coming into the river. Okay, so just do it. Again, the answers are in front of you. Just make sure you get the right answer. I need to check if you are raising your hand, so please raise your hands when you're done.
Ma'am, between which two attributes we have to sketch? We have to do the sketch.
Say that again.
Between which two attributes we have to draw the sketch?
Between which two attributes? I don't know. When I say sketch, I mean the river and the wastewater discharges. So what you need to do is just sketch a line for the river, and the two wastewater discharges are coming from both sides at the same point. You understand? River has two banks.
Yes, ma'am.
So let's assume that at point x is equal to 0, there are two discharges, one from the right bank, one from the left bank. So what will happen downstream and upstream? Got it? And assume mixing, assume instantaneous mixing at the point of discharge.
Yes, ma'am.
No hands? Taking a long time. Okay, good. I see a few hands. Very good. Let's move to the next one. And I don't know if I mentioned this or not. The K value has to be corrected for temperature. So under standard conditions, we do it at 20 degrees centigrade. If the water temperature is anything other than 20 degrees centigrade, then we use this correction factor. So for deoxygenation, the theta value is 1.047. And for re-aeration or oxygenation, the theta value is 1.024. And another thing that you can keep in mind is that raw sewage, which has large amounts of biodegradable matter, it has high K values, so 0.35 to 0.7. After treatment, the K value falls because the biodegradable part has been removed during wastewater treatment. And polluted river water for the same reason, because we are assuming that it has that whatever degradation has happened has already happened. So after a period of time, you will find similar K values. So that is about these K values. And I also wanted to say something else. Yes. So here are the reaeration constants for different water bodies. So small ponds and backwaters, you have the lowest K values. Low stream velocity, you will find intermediate K values. Uh, Very fast flowing streams. Now, what is the difference between a slow stream and a fast stream? The turbulence level in a fast stream is much greater than the turbulence level in a slow flowing stream. So, where the turbulence is higher, reaeration will be higher. So, swift streams, rapids, waterfalls, they all have K values around 1 or even higher. So it all depends on the degree of turbulence. So greater turbulence, greater mixing, and therefore your K value is higher. So there are two factors, degree of turbulence and temperature. Both of these will determine how fast the organic matter degrades. Then we come to more complex problems, and there is a fairly complicated problem here. You cannot do it in class right now, so that is your self-learning exercise. You will need to make a graph. I will be giving you an assignment as well. So in the next class, we will be finishing this topic, and we will also be having a test. I think I will have the test outside of class hours because I need at least another 1.5 to 2 hours to finish the remaining topic. And just be prepared that next week you will be having a test, not during class hours. It'll be a 1 hour test. It'll be open book, no talking to your friends, and that's all. So this is a problem that you need to do it on your own. Here is the last set of problems for the day, and then we'll close. So we have different wastewater samples. They've been analyzed for carbon, nitrogen, and phosphorus. In each case, you have to determine what is limiting. Carbon, nitrogen, sulfur, phosphorus, which one? Okay. So I'll leave it to you. And again, you can raise your hands when you're done. And please don't forget to finish your assignments before 31st. If you're done, you can leave. There's no problem with that.
Excuse me, ma'am.
Yes.
Ma'am, what is the type of question that are going to be asked in test?
So, what I'm doing in class, the MCQs that you have seen in the assignment, and most likely we are going to avoid descriptive answers. So, it'll be MCQ and numericals. Okay.
Okay,
It'll be,
ma'am.
even if we do descriptive, it'll be like one word, not one word, one sentence, very short answers. Because it's very difficult. We have 166 students. So it's difficult to grade too many descriptive answers. So it'll be MCQ type, mostly assignment type. Okay. And there will be a lot of numerical. So you can, I think your JE also has the same format, right? So it'll be numericals with MCQs.